Welcome to this presentation on Orbitals driven insights on the reactivity of boron oxide with dioxygen for methane oxidation on singlet and triplet spin states. This research was conducted by Parveen Rawal et al. And published in 2023. Today, we'll explore the key findings and contributions of this important work. Let's begin by understanding the problem this research addresses. Good morning, everyone. Today, we're diving into a fascinating area of chemistry that could revolutionize how we use one of our planet's most abundant resources, natural gas. Specifically, we're talking about methane, its primary component. Our goal is to turn this simple molecule into something much more valuable, like formaldehyde, a crucial building block for countless products, from plastics to medicines. But here's the challenge. Methane is incredibly stable, making it notoriously difficult to convert efficiently. Traditional methods often rely on expensive, rare metals. Did you know that over 70% of the world's natural gas is methane? Yet converting it into useful chemicals remains a significant hurdle for industry and sustainability. To tackle this challenge, we didn't just mix chemicals in a lab. Instead, imagine trying to find the fastest route through a complex city, not by driving every street, but by using a super detailed digital map that shows every turn, every hill, and every traffic light. That's essentially what we did with our chemical reactions. We used powerful computer simulations, a technique called density functional theory, to map out the chemical reactions on boron oxide surface, atom by atom. Our visual metaphor for this is a detailed 3D city map where different colored lines represent potential reaction pathways, and we're zooming in with a magnifying glass on the critical intersections. This allowed us to virtually test different pathways and see exactly how methane and oxygen interact with the catalyst without doing countless lab experiments. We started with a simplified model, found it wasn't quite accurate, and then built a much more realistic atomic level model of the boron oxide surface, like upgrading our city map from a basic sketch to a full GPS system, ensuring our predictions were as precise as possible. Our simulations led to a significant breakthrough, revealing the sweet spot for methane conversion. We confirmed that boron oxide can indeed act as a catalyst to convert methane into formaldehyde. The key lies in understanding how oxygen interacts with both the boron oxide surface and the methane molecule. We identified two main ways this reaction can happen, like two different roads leading to the same destination. But here's the big win: one specific path, involving a singlet form of oxygen, is dramatically more efficient and easier. It requires much less energy to get started, about 41.1 kilocalories per mole compared to 57.6 kilocalories per mole for the alternative triplet path. Crucially, this preferred singlet path avoids creating unwanted byproducts, specifically free methyl radicals, which often lead to less desirable side reactions. This means a cleaner conversion, focusing on our desired product, formaldehyde. So, what does this sweet spot mean for the real world? This research is a game changer because it shows that boron oxide, a common and inexpensive material, can mimic the catalytic power of expensive, rare metals, often called transition metals. Think of it. We could potentially use much cheaper and more abundant materials to convert methane into valuable chemicals. By precisely understanding the exact steps of this reaction, especially the highly efficient singlet pathway, we gain critical knowledge. This knowledge isn't just academic, it allows us to design even better catalysts in the future. This could lead to more sustainable ways to produce a wide range of valuable chemicals from natural gas, significantly reducing waste, energy consumption, and environmental impact in the chemical industry. It's about making chemistry smarter and greener. Looking ahead, how might this research impact your daily life in the next 5 years? First, imagine cheaper products. Formaldehyde is a key ingredient in countless items, from the durable plastics and glues in your furniture and electronics to disinfectants and even some medications. More efficient production means these everyday essentials could become more affordable. Second, expect a reduced environmental impact. 1. By making methane conversion more efficient and cleaner, we'll see less energy wasted and fewer unwanted byproducts. This translates directly to a smaller carbon footprint for many industrial processes, contributing to cleaner air and a healthier planet for all of us. Third, this fundamental understanding of boron oxide's catalytic power could inspire the development of entirely new environmentally friendly materials and processes, moving us closer to a truly sustainable chemical industry. Finally, better methane conversion means we can utilize our abundant natural gas resources more effectively, potentially enhancing energy independence and reducing reliance on less sustainable energy sources. This research is a small but crucial step towards a more efficient, sustainable, and affordable future.